Thanks for coming to this talk, and I know it's after lunch, so I'll try not to be myself and speak louder. So this is joint work with Rafael Frangelo and my advisor, Bo Wagner. First, I'm going to give a little bit of motivation and then talk about the general model and the results. We started out by asking, if so many trillions of dollars are being traded in just Uniswap alone, are there theoretical justifications for using constant function market makers instead of any other kind of AMMs? So, and are there better ways of implementing an automated market maker? So just as a heads up, the answer is no. We show that CFMM is the best way to implement an AMM in some sense. And I'm gonna walk you guys through the result. So I'm sure a lot of people know constant function market makers in this crowd, but just to recap, it's a way of implementing an AMM such that so that the market maker defines a predefined potential function phi, and a trade is actually carried out or not depending on whether the function value remains constant before and after the trade. So in the Uniswap case, this function phi is the product rule. So if you start out if you have reserves 1, 2, and you can execute a trade 1, -1 because it gets you back on to the same level curve, and so any trade in that red curve is actually possible, and it's called an indifference curve. So to ask what is the best way to implement an AMM, we have to step back and think of what an AMM does. It's this general centralized mechanism that trades with both with sellers and buyers instead of them having to match with themselves. So for example, foreign currency exchange websites could be viewed as AMMs to some degree. Other kinds of AMMs are prediction markets, which trade securities of future events. And I'm going to talk about this on the second half of the talk. And your beloved Uniswap is also an AMM. So to put a general framework, let's say you start out with n assets. You don't have to restrict to 2. A trade in this framework would be a n-dimensional vector, RT, at time t, and positive coordinates of this vector kind of signify the amount of assets being given to the market maker, and the negative quantities taken away from the market maker. So you can represent a trade in just one vector. When we say history, we mean a sequence of trades, valid trades that have happened so far in time. And a trading rule, which is the crux of an AMM, is a function valid trades, which takes in this history of valid trades that have happened so far and outputs the set of valid trades at this point of time t. So observe that CFMM is actually a subcase of this general model when you restrict the val trades by the function phi, given we saw the way we restrict is by restricting it to a single indifference curve using phi. So we start out with this general model, and we're going to look into axiomatic characterization result first, and our results are threefold. For the first one, we're going to ask, any characterization is going to ask this question: what constitutes a good market maker? Or alternatively, how should we design this valid trades function? It could be any function. It could map a history to actually a set of trades. And we start by proposing some basic axioms for effective trading. So the first axiom is called no-dominated trades. It says that a market maker should not offer a trade and also a strictly better offer worse off trade. Why? Because a rational player would not choose the worse off trade if given a choice. And this just is justified by the rationality of the trader. The second axiom is called path independence. it says that if a trader performed trade R and then immediately R prime, it should be the same as the trader performing R plus R prime because this kind of eliminates cases where the trader might find it profitable to split their single trade into multiple smaller infinitesimal trades and kind of profit from it. And this just eliminates that scenarios and the overhead that causes to the market maker. So we show that no dominated trades and path independence put together gives no arbitrage condition that hopefully some of you are familiar with. It's not very important for this talk. So the third axiom is called liquidation. It says that a trader should be able to buy or sell any bundle for some fraction of any other bundle. This just encourages better market functionality when a market maker is able to trade anything for anything. The fourth one is demand responsiveness, which says that the price has to respond according to the demand. So if a trader requests a bundle R for some amount of asset 1, let's say, the next time the trader comes in and requests R, it should cost more in terms of the price the trader pays to the market maker. So our first result shows that a market satisfies all these 4 axioms, which hopefully we can agree that they're kind of pretty basic for a market to function. And it satisfies all these 4 axioms if and only if it's implemented using a CFMM with an increasing concave phi. So it kind of justifies, so yes, DeFi world was correct in choosing CFMMs. That's kind of a good theoretical justification for it. So the basic proof idea is we can use liquidation, no dominated trades, and path independence to kind of narrow down the set of the functions into a single curve instead of having an indifference band, because you can eliminate a lot of those scenarios by no dominated trades and path independence. And a continuous one because of liquidation. And the demand responsiveness is the key for making that function concave. I want to quickly note that there has been some prior literature in CFMM world which does talk about axiomatic characterizations, but they build on top of a CFMM structure, whereas our axiomatic work kind of builds on any very general AMM and arrives at a CFMM. So moving on to, just to recap, we started out with the general AMM, and once we ask for very basic market properties to be satisfied, we get a CFMM with increasing concave phi. So moving on to the second result, I'm going to talk about how these are equivalent to prediction markets. Before that, let me introduce briefly what prediction markets are. Let's say you have a horse race, and you want to create a market that allows bets on these horses. The way you would do that is to create one security for each horse winning. So let's say security A, if you hold one security A, you're going to get $1 if the left horse wins and 0 otherwise. And similarly, since it's an arrow Debreu market, you create one security for each of the horses because you want the set of securities to be exhaustive and mutually exclusive. So the reason this is called prediction market is because, let's say the price the security C is trading is 0.3. But for some reason, you as a trader believe that it should be 0.5 because you have some, let's say, insider information on the horses. You would buy the security C until it reaches the price 0.5. So this is obviously assuming that there are no budget constraints. So by engaging in trading and moving the price from one to the other, you're kind of conveying your internal belief about that horse winning, and a prediction market accumulates these beliefs in an effective way to and uses those predictions for its own purpose. The primary approach in the prediction market literature is to employ what is called a cost function, which is convex and once invariant, and it's a cost function C, which is convex and once invariant. The way the prediction market proceeds is at round T, there's a state of the world so far, which is the total number of securities of shares sold so far, QT minus 1. A trader comes in and requests a bundle of securities RT. The market updates its state to QT minus 1 plus RT. And in order to get this bundle of securities RT, the trader has to pay C of the current state minus C of the past state in cash to the market maker. So this has been pretty well studied, and right off the bat, they seem very different frameworks for implementing an automated market maker. In prediction markets, you trade securities for cash, and in CFMMs, you trade between assets. In prediction markets are especially designed to elicit forecasts from traders, whereas CFMMs are designed to just trade assets and provide liquidity. In prediction markets, any bundle can be bought or sold for some amount of cash, versus in CFMMs, only the set of allowable trades is very restricted to the indifference curve that we saw earlier. And it was believed in the CFMM literature that both these entities are different and they diverge. We actually show that that's not the case. This is our second result. In a strong sense, we show that CFMMs and cost function market makers are actually equivalent via this map. So there's a one-to-one map to go from one to the other. And when we say equivalent, we mean that at any given point of history, the trades available in these both worlds would be the same. So the kind of market progresses in a similar fashion. I'm gonna skip over proof because of time. It does use risk measure literature in convex analysis. So if we apply, we are in a Uniswap conference, so we have to apply it to the Uniswap function. So if we do that, we get that cost function. So this is interesting because that cost function actually appears in Chen and Pennock 2007 in prediction market literature, and it's termed as constant log utility market maker. And the corresponding proper scoring rule for that cost function looks something like this. This also appeared in prediction market / machine learning literature in Buja et al. 2005, and it's termed as boosting loss scoring rule. So you can see that this kind of like bridges the two literatures, and there were similar entities present in the prediction market literature as Uniswap. So just for people who are not familiar with scoring rules, let me introduce them. So they're a mechanism to score predictions made by agents. So if an agent makes a prediction, if there is a future event E, and an agent makes a prediction P about the event, let's say the event happens and the outcome Y is realized of the event, the agent is paid or scored S of P of Y. And this scoring rule is proper or truthful if and only if it's incentive compatible for the agent to actually report its true belief about the event, and the agent has no incentive to lie about their belief. So the interesting part is the implications of this equivalence. Like I mentioned, now we have a tool to go from one literature to the other, from prediction markets to CFMMs, and we hope that it makes people look into borrow things from each of the literatures to the other. And hopefully this encourages new CFMM designs as prediction markets have been well studied. And on the other hand, hopefully prediction market folks take away the new innovation of liquidity provisioning from CFMM world. So I talked about how, this is Abernathy et al. 2013, which kind of has a similar axiomatic flavor. They start with a general AMM and kind of impose some basic elicitation properties. And from these elicitation properties, they show that the only way to implement that is via a prediction market with the cost function C. But I also talked about in our first result that if you start with desirable market properties, you end up with a CFMM, right? In the second result, I talked about how there's a one-to-one correspondence between prediction markets and CFMMs. So that has to take us back to this connection between these two. So it kind of illustrates how the elicitation properties in a market are tightly correlated to the desirable market making properties. So CFMMs can be thought of as eliciting something. And what are they eliciting is this relative future valuations of assets. So moving on to the third result. So I talked about going one from one to the other, but it only talks about taking one indifference curve and making that another indifference curve in the other. Let's say if you start from the cost function, it takes one cost function and makes it one indifference curve of the phi. But if you were to extrapolate it, since cost function is once invariant, it extrapolates like this. But the problem is the assets going in the negative quadrant doesn't really make sense, even though it makes sense for securities to be in the negative quadrant. So we impose a fifth axiom called bounded reserves, which says that at no point of history should the reserves actually be reserves should be negative. So we also, let me define liquidity. It's the amount of assets available to buy or sell around a given price that does not cause drastic price changes. So the red curve has very small liquidity, and as you move up, the liquidity kind of increases. So this property is kind of desirable because the bigger the market, the more liquid it should be. So the goal for this result was to propose a phi for a single cost function that kind of has both the properties of bounded reserves and liquidity scaling property. So we give this construction that kind of does that. So if you start out with a cost function that's convex, increasing, and once invariant, you can get a phi that satisfies all these properties, and it has this nice liquidity scaling property as well. So that's what we show. And this phi obtained via this is concave increasing and once homogeneous and satisfies all those 5 axioms. We also show that every concave increasing one homogeneous CFMM is a result of construction 1. So as you guys might be familiar, most of the practically implemented CFMMs are increasing concave and once homogeneous. So this is like you could think of an oracle of constructing new CFMMs with those desirable properties. So that's it. To recap, we show that we characterize ideal market maker, and it results in a CFMM. We show an equivalence between CFMMs and prediction markets, allowing for transfer of literatures. And we give a construction of resource-aware CFMM and prove that most practically used CFMMs are actually obtained via this construction. And for future directions, we actually use the results of this paper to propose general liquidity provisioning protocols and give some interesting insights in our latest work. And it could be interesting to look into how introducing transaction fee could give you an adaptive liquidity kind of framework. And further connections to prediction markets could be explored because prediction markets has literature that deals with if, let's say, assets has predefined relationships, or in how does like the prediction market deal with combinatorial versions of these assets. Thank you. According to the equivalence, we should, because information is tightly correlated to good market making. So it does not make too much sense. When you're thinking of just assets, trading assets, I think demand responsiveness makes more sense because, oh yeah, if like demand for a certain good goes up, the price has to go up. It's more simpler compared to what you're mentioning is information incorporation into the mechanism, which is more of a prediction market axiom. So I guess the aim is to have least number of axioms. And maybe you could just have information acquisition and still get the same result, but I'm not sure.
CFMMs have certain inertia, and actually more liquidity, the more inertia there is. And arbitrage solves that to bring it to reality of the market. Now, if you have prediction markets, how do you tune them to reality? I know of UBET, prediction. What they do is they calculate probabilities and they incentivize movement towards the theoretical probability. Anything you can suggest there?
This is pretty like vanilla model and does not consider all those frictions. So the way this prediction market works is just starting from zero and let the agents decide. So I'm not sure if how one would introduce frictions in it. The reason the bigger trade is profitable over smaller trades is when you introduce fees. But without the fees, which is our model, it should be the same.
Fine. Thank you, speaker again.